Hello everyone, welcome back to the channel. So today I'm gonna talk about machine learning. So which is a very interesting topic yet important in data science. So let us start the session by introduction to the machine learning. So basically this machine learning is a subset of artificial intelligence focused on building systems that learns from data and improve their performance over time. So without being explicitly programmed, it involves developing algorithms and statistical models that enable computers to perform tasks by learning patterns from data rather than following predefined solutions. So basically, if it has to be when we feed the data to the machine learning model, it will create or it will learn the patterns within the data and it will predict some outcome. So that is so, and machine learning is a subfield of artificial intelligence. So here you can see how it got divided. So, and this is a generative AI. Then next comes deep learning, then machine learning and artificial intelligence. So let us go through one by one in a simple way. So artificial intelligence, nothing but it involves techniques that equip computers to emulate human behavior. So enabling them to learn, make decisions, recognize patterns, and solve complex problems in a manner akin to human intelligence. So just like how in day-to-day life nowadays we are using this chatbots. So these are all the applications of this artificial intelligence. So we could see a lot of improvements in coming days as well on this artificial intelligence. So let's not talk about more about it and let's come to machine learning. And machine learning is subset of AI and uses advanced algorithms to detect patterns in large data sets, allowing machines to learn and adopt. ML algorithms use supervised and unsupervised learning methods. So supervised nothing but labeled, unsupervised nothing but unlabeled data. So we will talk about in detail about how supervised and unsupervised learnings are. So that is how this machine learning thing works. That is about machine learning. And for about deep learning, so deep learning is a subset of ML which uses neural networks for in-depth data processing and analytical tasks. So deep learning leverages multiple layers of artificial neural networks to extract high-level features from raw input data, simulating the way human brain perceive and understand the world. So this deep learning is just like our human brain, how these neurons, neural networks, how our human body will work. So in the same way, this deep learning was designed with the neural networks. And next is generative AI. Generative AI is a subset of deep learning models that generates context like text, images, or code based on provided input. Trained on vast data sets, these models detect patterns and create outputs without explicit instructions using a mix of supervised and unsupervised learning. So that is how this generative AI, deep learning, machine learning, and this artificial intelligence, the a basic definition or a quick overview of this all four things. So let's jump into the machine learning, our main topic. So this is a normal flow chart how the machine learning works. So we do have work with a lot of machine learning algorithms and how the machine will learn from the data and how it get improved, how it gets analyzed, and how this neural network works. And when we need to work on some classification data or some continuous numerical data, so data mining, so all these things, this is normal simple what are all the things related to machine learning, the image that shows all these things. So the key concepts. So we are gonna talk about a few acronyms, or I can say that a few words in machine learning, where we are coming across when we are building a machine learning model or evaluating the model. So we are gonna use these common keywords in entire session or whenever we are working on any ML models. So that is why I mentioned separately all these key concepts. So data is nothing but that is a foundation of machine learning. So everything data is like it is the starting point, and that is the main important thing. Whenever we feed the raw data, then the machine will look the understand the patterns, and it will predict the output. So basically the data, it is a main fundamental of machine learning. It can be structured, example databases. It can be unstructured also, example some text, uh, un, and images, like where we are not able to recognize that image. So those are not a structured way. So data can be like sometimes we have a structured data where we are able to understand it. Sometimes we may come across unstructured data of texts or images. So these kind of things will come across in machine learning whenever we're talking about this data. And next comes algorithms. So algorithms, nothing but we do have a lot of algorithms, but we are going to talk about very few algorithms in this session, and in coming sessions we are going to talk about one by one all the advanced algorithms. So in this tutorial I'm going to cover some basics algorithms which most of the times we can use. So algorithms, nothing but the method used to analyze the data and extract the patterns. So we should the by given the input raw data, this method used to analyze the data and extract the patterns. The common algorithms including linear regression, decision trees, support vector machines, and neural networks. So these are all the common algorithms in this machine learning. And next thing is model. This is a representation of what has been learned from the data. So we feed it some raw data, then algorithm was applied, then then the model, we are creating a model, the representation of what has been learned from the data. So what has been learned from the raw data, the model is trained on data and then used to make predictions or decisions. So for example, let me give an example where, so I have a car. I just wanted uh, so for the car, the features are like the model of the car and the fuel type, and also on-road, off-road, something like that. So these are all comes under the features, and depends on these features, the car value, cost of that car value, that is a target variable. So that is how when we feed this kind of data to predict the final price of anything. I just gave example for the car price, so we can predict bike prices or house prices, something like that, by giving some raw data. And the model itself, it will learn from the input data. Then when we give a new data set, and it will predict based on the historical data patterns. So that is how it will work. So that is what this training means, the process of feeding data into the algorithm to develop a model. And the model learns by adjusting parameters to minimize errors. So whenever we feed the raw data, so it will train, and the model learns by adjusting parameters to minimize errors. So that is about training and testing. So whatever the training, evaluating the performance of a model on new unseen data to ensure it generalizes well. So for example, with the same example, so I fed the data of car price. Now I'm giving new features like a new model, and also new the engine type, or off-road, on-road, or electric. This time fuel type I'm giving electric engine, something like that. So, and I wanted my model to predict the outcome with these new features. So that is how we will test or evaluate the performance of a model on new unseen data to ensure it generalizes well. And the features are nothing but like the car. For example, in the given example, the features of the car, the model, like is it a 2017 model or 2018 model, 2020 model, 2024 model, and the final price is depends on this input features. So that is how the features, the individual measurable properties or characteristics of the data. Feature engineering involves selecting and transforming these features to improve the model performance. So basically the features nothing but the input variables and the labels. The output or target variable that the model is trying to predict. And in supervised learning, labels are provided during the training. So for example, labels, so I can show some image here. So here I'm feeding this data with some labels, nothing but I'm giving. So if my this object with this characteristics, so I'm giving a tomato as the name, and with this characteristics I'm giving a label as carrot, and with this characteristics I'm name this object as bell pepper, something like that. Labels nothing but tags. So in supervised machine learning, so we will use this labels or tags. And evaluation matrix like measures used to assess the performance of a model, such as accuracy, precision, recall, F1 score, and mean squared error, absolute mean square error, and root mean square error. So we have this evaluation matrices, so that we can evaluate the model, how it is performing. Is it a good fit or bad fit, something like that. So these are all the basic terminologies, so we are going to use in all in machine learning algorithms or machine learning models. So whenever we wanted to talk about anything about machine learning, so we are going to use all these terminologies. Okay, so let's talk about different types of machine learnings. Out of types of machine learning, so the first thing is supervised learning. So the algorithm is trained on labeled data in presence of supervisor, something like that. Supervised nothing but, so I am just giving the data with the labels, so I'm just feeding the machine with the input data with some labels. So I'm giving this object as with the characteristics, so it is a tomato and it is a carrot and it is a bell pepper. I'm only telling the machine, and in future if I give the same object, the machine has to predict based on the data I feed in initially. So that is how this supervised machine learning works. Supervised machine learning is a branch of artificial intelligence that focuses on training models to make predictions or decisions based on labeled training data. So here you can see this is my input data and with the labels. So these are my labels. Because here I have three kinds of vegetables, so like carrot, tomato, and bell pepper, and I'm feeding the data with the labels. So a object with this characteristics, it is a carrot, and I'm telling the machine or model that if the object is with this characteristics, it is a tomato, and object with this characteristics, it is a bell pepper. So I'm feeding the data with labels, and here machine has to predict based on this data. If I give the new objects also with the similar characteristics, machine has to predict by learning by after training this data. So that is how here the prediction will comes. So this is my test data. If I wanted to test on a new objects with similar objects or new objects I'm feeding to the model prediction, then it will predict as okay, an object with this characteristics, it is a carrot and it is a bell pepper and it is a tomato, something like that. So this is how the supervised machine learning will works. So that is about supervised machine learning. And so we do have different types of supervised machine learnings. One is classification. Classification nothing but the above example is comes under classification only. Like categorical labels, so carrot, tomato, bell pepper. So this kind of data, if you are feeding or if you are working this kind of data, then that is comes under the classification problem. It could be spam or not spam. For example, whenever in our emails, so a lot of times we might get a lot of spam emails, right? So it can be utilized this supervised machine learning, whether it will segregate my emails into a spam with some characteristics and not a spam email. So in for future, if I get a new email, the machine will it has to predict that based on the previous historical data. It will predict that okay, if this has the characteristics of spam, then it will be sent it to the spam folder. If this is not a spam, it is a regular email, then it will be sent to the normal inbox. So that is how, that is an example of classification problem in supervised. And regression, nothing but predicting a continuous value. Example, I gave some car price prediction, bike price prediction, or house price predictions. So that comes under this regression models. So we have supervised models like classification and regression. Okay, that's about supervised machine learning. So let's jump into unsupervised machine learning. So in unsupervised machine learning, the algorithm is trained on unlabeled data. It tries to identify patterns and structures in the data. So here you can see the image. So here I am feeding data to my model without any labels. The model has to understand by the characteristics of this object or the input features. So here the model, when I feed the input data, it will segregate into the clusters, like object with this kind of characteristics or features. So it will be clustered into dogs, or object with the different kinds or something like that, it will be segregated into cats, something like that, without giving a label. Unlabeled data, machine has to prepare, or it has to identify patterns and structures in the data. So that is how it will work. Supervised machine learning with the presence of labels. So in unsupervised machine learning, we are gonna feed the model without any labeled data. So that is how. And the machine, the clustering, group the data points into clusters. These are nothing but the clusters. Similar kind of characteristics objects will be segregated in a one cluster. Example, customer segmentation, like different types of customers. When we are working on a customer data set, so it will segregate the customers based on the uh, like their work or something like that. And the finding rules that describes a relationship between features. Example, market basket analysis. So the examples of this unsupervised learning. And next comes semi-supervised learning. So it is combination of labeled and unlabeled data. Sometimes when I have data partially with labels, and other data without the labels, and machine has to learn the patterns, improve the learning accuracy, useful when labeled data is scarce. So here you can see here that I am giving some input data with uh, some objects with the labels, and different objects are without labels. A machine has to this machine will when I feed the input data, the model will be prepared with the input data by looking at the patterns and the characteristics of the objects. Then machine will predict. So if I have this labels, so obviously machine will predict, okay, this is an orange and this is a banana. But this is like with this, we are feeding this data without any label. So that the machine will process the data here, then the machine will be able to understand, okay, this is a new item, and by looking at these characteristics, okay, this is a new item, then it will predict. It's like an apple. So this is how a semi supervised learning will work. The combination or combined labeled and unlabeled data. So that is about semi supervised learning. And the next comes reinforcement learning. The algorithm learns by interacting with an environment and receiving feedback in the form of rewards or penalties. It aims to learn a strategy that maximizes cumulative rewards. Example, game playing and robotics. So for example, here you can see in the image, so this is my raw data. So here it will interact with the environment, and it will uh, give the feedback if it is like model is performing better, or so if my this is my output, it has to get, if I give this input and this environment, and receive feedback in the form of rewards. Like if it is this data can be segregated into this clusters. So if it is going to the incorrect cluster, then it will send a feedback, or if it is going good, then it will give a reward, something like that. So that is how this reinforcement learning will work. Okay, so this is what we have so far. We covered supervised machine learning and unsupervised machine learning, semi-supervised machine learning, and reinforcement machine learning. Uh, Supervised means data with labels, and unsupervised learning means without the labels. Machine will predict the patterns inside the raw data. And my second thing, the third thing is semi-supervised. The combines labeled and unlabeled data. And reinforcement learning is like it will uh, interact with the environment, and it will receive feedback in terms of rewards and penalties. So that is a brief overview of four types of machine learnings. So the applications of this machine learning is like, so we do have number of applications in today's world. So it is using in healthcare, like disease prediction and personalized treatment plans, medical image analysis. This medical image analysis is nothing but example case. For example, if I wanted to look at the cancer tumor, the size of the cell, something like that, the severity of the cancer, something like that. If I pass that data set of cancer, then the machine will look at the patterns, then it will predict. So something like that, that is a normal example case where we are using in medical field. And the finance field, the fraud detection, like in banking sector, something like that, fraud transactions, credit card transactions, something like that, and algorithmic trading, credit card scoring, something like that. So we are using in finance sector. And marketing sector, the customer segmentation, how the customers, based on the customer purchase history or something like that, we are using this machine learning models. And this recommendation systems. For example, you might be wondered whenever you're browsing YouTube or Netflix or some streaming platform. So whenever you watched a adventurous movie or action drama, something like that, so you will see some advices, like you will get some recommendations based on the your history. So if you watched some adventurous movie, for example, let's give an example. So if you are searching for Harry Potter movie, so you might get similar recommendations like Lord of the Rings, something like that. So that is how this recommendation systems works. And sentiment analysis. And in transportation, autonomous vehicles, route optimization, traffic predictions, and we have natural language processing, language translations, like from one language to other language translations, and chatbots, sentiment analysis, and computer vision, image and video recognition, object detection, and facial recognition. So we do have a number of applications in today's world. So these are all the just basic examples where we are using this machine learning models. So let's jump into in detailed supervised learning algorithms. So the first thing is linear regression. Linear regression, the first algorithm from the supervised machine learning. Okay, the linear regression, the purpose is like used for predicting continuous numeric values. And the model, it models the relationship between a dependent variable and one or more independent variables by fitting a linear equation to observed data. So the example use case is like predicting house prices based on features like size, number of rooms, and location. So for example, if I wanted to predict a house, then the input features like the size of the house, how many bedrooms are there, something like that, how many square feet, and also how many rooms are there. But is it a 1 BHK, 2 BHK, 3 BHK? So obviously, based on that size of the rooms, the price will be differ, right? And also the location. It could be depends on the location. Also, the house value changes. So that is what if I feed data something like that, it will predict the price of the house. So by using this linear regression model. So here we do have the dependent variable, which is nothing but a target variable. The variable we want to predict. So house price, the house price we wanted to predict in the given example. So that is a dependent variable. It will depend on the size of the house, number of rooms, and the location. So in the given example, so these are my independent variables. So independent variables, nothing but the variables used to make predictions, and the target dependent variable is the value to predict the house value, and the features size, number of rooms, location, these are independent variables. They are not dependent on anything, they are independent variables. So this is my linear equation, y is equal to beta 1 x plus beta naught, something like that. So y is equal to mx plus c, same linear equation. When we are in a mathematics class, we used to work on this y is equal to mx plus c, right? So same equation we are going to use here. So here the y is the predicted value, my output or predicted value, and beta naught is the intercept. Beta 1, beta 2 are, these are the coefficients, and x1, x2, x3 are my number of input features. So these are nothing but independent variables. So y is a dependent variable, y depends on x. So is there any change in the x, that will, the y value will be changed, and that is the reason why y is called a predicted value and a dependent variable, and this x values are independent values, input features, and this e is nothing but the error term, residual. So I took some example, I just wanted to explain the same, this linear regression whatever we discussed. So this is how we will use in this is how we can make a model and fit the data, something like that. This is a basic data set. So I just wanted to show with a simple data set. So here uh, I'm just importing all the necessary libraries like NumPy, Pandas. So this is sklearn, scikit-learn, so which is one of the very powerful library for machine learning. So we have to import a lot of things like sklearn.model selection. So if I wanted to train and test the data, then I need to import this train test split from the sklearn model selection, and from sklearn linear model I have to, because we are talking about linear regression, so I am importing the linear regression from the sklearn. So this is like a library where you will have all the machine learning things will be there. So you need to import all the required like models, or this uh, this mean squared error or auto square or accuracy precision, all these things are there in sklearn, all these matrices also. So you need to import it from the sklearn. So I'm going to prepare a separate video on this sklearn, the scikit-learn library. So for now, so this is how I imported a train test split, and this is my model, linear regression. So this is to evaluate my model, how the model is performed after fitting the model. So mean squared error and R2 square. So this is my sample data set. So I'm giving the feature 1 and feature 2. So these are my feature values. For example, if I take the above example, so I could say that these are like my house, number of rooms and size of the houses, or I can say uh, we have number of rooms, and okay, let's take the size of the house and size of the number of rooms, and this is like a price of my house. So, normal, the feature 1, feature 2, and target variable. So this is my data set. So this is how I just created, I passed this data to, so that my data frame created. Now I have to split this data into training and testing set. So I have to split it with the input data. So I'm giving x is equal to this features. The features, feature 1 and feature 2, these are my input features. So I'm just splitting input features and output, so that the machine will train and it, train the model. So the my y I'm giving a target variable. So this is my output, the predicted value, and these are my features. So x is equal to feature 1, feature 2, and y is equal to I'm giving target. Then x train, x test, y train, y test. So since I imported this train test split, so if I apply this train test split, and if I pass my x and y variables, and I'm giving this test size random state, I'm giving 42. So if I like if I run this line, then the data will be splitted into training set and testing split. So here I wanted to test 20% of the data. So if I take this entire data as 100%, so 80% data used for training purpose, and the remaining 20 will be tested, whatever the machine trained. So based on the training, I wanted to test this remaining 20%. So here I wanted to create and train the model. So model is equal to, since I imported linear regression, so model is equal to linear regression. Then I'm fitting the model dot fit. Then I'm passing my x train and y train. Then the model will be fitted. With the trained model, I wanted to make some predictions. So ypred is equal to model dot predict. So these are all the basic syntaxes, like x train, x test, y train, y test, to split the data into testing and training. And this is a syntax for like to create and train the model, just a model name. Then if I wanted to fit the model, then model dot fit, then you need to pass the training data like x train and y train. Based on the fitting this model, model will do some predictions. So ypred is equal to model dot predict. So if I pass the remaining 20%, test size I'm giving 20%, right? So I'm passing those 20, the 20% data here, then the machine will make some predictions. So this is how the machine will do some predictions, and after that we need to evaluate the model, how the machine predicted the actual values versus the predicted values. So we can evaluate the model by doing this mean squared error, y test and y predicted value. This is the testing value and this is the predicted value. These are like existed values, and these are the predicted value. So based on these two parameters, the mean squared error R2 score. So this is how we can evaluate the model. So here in detail we'll talk about this mean absolute error, something like that. So this is how we will create a machine learning linear regression model, and we can fit the model by using train test split, and we can do some predictions based on the given data, trained and data. Then we will do some testing. So this common evaluation matrix for linear regression. So evaluating the performance of a linear regression model involves using various matrices that quantify the accuracy of the model's prediction compared to the actual values. Here are some of the most common matrices. Mean absolute error. This is nothing but a normal, the measure of average of absolute difference between the predicted and actual values. So for example, my predicted values are 1 2 3 4, so it will take the mean of those predicted values and the actual value data set mean. The difference between the mean values of this predicted and actual values, which is nothing but a mean absolute error, and it provides a straightforward measure of average error, so less sensitive to outlier compared to MSE and RMSE. Lower MAE indicates a better fit. So here we got the mean squared error is 1. So basically after the model is predicted something, then I wanted to look at this mean absolute error. If I get a lower mean absolute error, that indicates a better fit. That means the model is performing better. And the next is mean squared error, the measure of average of the squared difference between the predicted and actual values. This is a normal difference. This is a squared difference. That is how we can calculate the mean squared error. And the lower MSE indicates a better fit. So here also, if I have a lower MAE, mean squared error, then that means the model is fitted or performing better. However, it is sensitive to outliers as it squares the errors. And the next thing is RMSE, root mean squared error. The root mean square error is not provides an error matrix in the same units as the target variable. So it is root of mean squared error. That is how we can calculate a root of mean squared error, and easier to interpret compared to mean squared error since it is the same units as the original data. Lower RMSE indicates a better fit, and R squared, R2 square, represents the proportion of the variance in the dependent variable that is predicted from the independent variables. So it the values ranging from 0 to 1, 1 nothing but a perfect fit. So in the above example, I got auto square is so 1 nothing but a perfect fit, and 0 nothing but model does not explain any of the variance, and 0 model is less than 0 is model is worse than the horizontal line mean of the target value, something like that. So this is a linear regression line. So this is how you can see, these are my combined features, feature 1, feature 2, and this is my target variable. So these are my data points, and this is the predicted output. So this the distance between the my original data points and the predicted value, this is the error. So this is where we can calculate the mean absolute error, mean square error, root mean square error. So the difference, the line will be fitted so that the distance between the points is very less. So this is how we can fit the regression line. And that is about fitted linear regression line that represents the model predictions. So that is about a linear regression with a simple data set, and how to prepare a linear regression model with the sample data, and the evaluation of the simple linear regression model. So next we will gonna talk about a logistic regression. Logistic regression is a supervised learning algorithm used for binary classification problems, where the target variable is categorical with the two possible outcomes. So it is a type of regression analysis that predicts the probability of an outcome, which is then mapped to discrete classes. Binary classification, nothing but the output is like has only two classes, like yes, no, true, false, or a spam or not spam, default or not default, something like that. I have only two classes, two categorical variables. So that is a binary class classification. So logistic regression is used to classify the input data into one of the two classes. Example, spam or not spam. Only two classes we have. That is where we will use this logistic regression, default or not default. So here we will use, so above we used to evaluate the model, we used mean squared error, absolute mean square error, R2 score. So here we are gonna use logistic function, sigmoid function. The core of the logistic regression is the logistic function, which outputs as a value 0 and 1, because it is a binary class classification, either 0 or 1. Only two categories, no third category. So this is the formula how we can calculate the sigmoid function. Sigmoid is equal to 1 by 1 plus e power of z, where z is nothing but again a linear regression line. The above we discussed a linear regression line. So beta is nothing but intercept, and these are called the input features. So that is how we can work on this binary class classification problems by using logistic regression. So this is the details about the logistic regression, and here comes a sample data set how we will use this logistic regression. So I just imported all the basic necessary libraries. So here again I'm using train test split to train and to split my data, input data into training set and testing set. So this time I'm gonna use logistic regression from sklearn.linear model, then sklearn.matrix. So here I'm using accuracy score precision to evaluate the model, recall score, F1 score. So these are all like to evaluate the my logistic regression model. So this is my data set, input feature 1, feature 2. So here you can see my target variables are only two class, either 0 or 1. So that is my simple data set. So this is my DF. Now I just wanted to split the data into training and testing sets by using X is equal to my features are my input variables, and my Y is target is nothing but my output variable. So X train, X test, Y train, Y test, train test split, X comma Y, same thing. I wanted to train 80% and I wanted to test 20% of the data, and random state I'm giving 42. So again, same model is equal to logistic regression model dot fit I'm passing my X trained data and testing data so that the model will be fitted. And with that model, I'm gonna make some predictions. So I'm passing this remaining 20% of X test data so that the machine will predict. And this is how the machine will predict. Model dot predict. And this is how we can evaluate the logistic regression model accuracy score by passing y tested value and the predicted value, the test original values and after the predicted values. Precision, same. Precision score, y test, y pred, and recall f1 score. So this is how we can evaluate the model. So if I wanted to show the sigmoid curve by using a above model. So this is, I plotted this figure by using the matplotlib. So that is why I imported matplotlib as pyplot. So I just wanted to see the this is how you can see a receiver operating characteristic ROC curve. And if you wanted to see this, so accuracy means the proportion of correctly classified instances out of the total instance. So I have two instances, either 0 or 1. How the machine is predicting, how the model is performing, is it predicting correctly or not? So that is where this accuracy will come. And precision, the proportion of true positive predictions out of all positive predictions, useful in cases where false positives are costly. So that is where this precision will come. And recall, the proportion of true positive predictions out of all actual positives, important in cases where false negatives are costly. And also F1 score. So this is how you can evaluate the model by using accuracy, precision, recall, F1 score, ROC curve. So by look, this is the ROC curve. So I wanted to see a sigmoid curve where, because my binary class classification, how the data is behaving. So that is why I took an example with only one feature and target variable, and I prepared this my logistic regression model. I splitted the data into training and testing. Then, so if I run this my model, so this is how my sigmoid curve. So these are the values where output is 1. These are all the values where my output is zeros. So this is my sigmoid curve, 0 and 1s. This is how it look like, sigmoid curve. The the I mean blue dots are my original actual data, my training data, and this is like a predicted output. So the difference between these is like my evaluation of matrix will comes into picture. So this is how logistic regression will work on binary class classification. The advantages of logistic regression is like the simplicity, easy to implement and interpret, and the efficiency. Compute computationality efficient for binary class classification problems. Probability output provides probabilities for class membership, useful for decision making. And feature importance coefficients indicate the importance and direction of each feature's impacts. So these are all the advantages of logistic regression. So next comes decision trees. So decision trees are a popular supervised learning method used for classification as well as regression tasks in machine learning. So they are powerful because they can handle both numerical and categorical data. And they require relatively little data preparation compared to other algorithms. So whereas we discussed about a logistic regression and also linear regression, in linear regression, we are working on only the numerical data. And in logistic regression, we are working on a class binary class classification. There are two categorical variables only, either true, false, spam, not spam, something like that. But whereas in decision trees, it will work on both numeric as well as categorical data. And this algorithm requires relatively little data preparation compared to other algorithms. So this is how this will work. So this is a basic decision tree algorithm. So here you can see, and the tree structure. Decision tree is a hierarchical structure consisting of nodes and directed edges. Each internal node represents a decision. Like this is a node, and each again it represents a decision, yes or no, something like that. It can be more. So decision based on a feature value, and each leaf node represents the outcome or a decision. Nodes nodes are split based on features such that similar instances are grouped together, like clustered together, something like that. Similar instances. And splitting criteria, the decision of how to split nodes is based on metrics like Gini impurity and for classification, or variance reduction for regression. The goal is to maximize homogeneity, reduce impurity in resulting nodes. The predictive power, decision trees are capable of learning nonlinear relationship between features and target variables. Not only linear, it also capable of learning non-linear relationships between the features and x and y, like features and target variables. They can capture complex patterns in the data and handling overfitting. For example, if my model is overfitted, it can handle. Left unchecked, decision trees can overfit the training data, capturing noise along with signal. Techniques like pruning, reducing nodes with a little impact, and setting minimum samples for leap or maximum depth can mitigate overfitting. Classification problems, for example, the applications of the decision trees are like in classification. So we do have predicting categories like whether the email is a spam or not. In regression, predicting a continuous value like house prices. We can use this decision tree machine learning model also for regression problems. We can use this decision tree model for classification problems also. So that is the advantage of this decision tree model. So this is a sample example in Python using scikit-learn model. So I just used this basic libraries, and this time my model is decision tree classifier plot tree. So this is my model, and these are evaluation matrices like accuracy score, classification report. So this is my sample data set where the target variable has the classifications of zeros and ones. So this is how the same syntaxes for all the machine learning models. In the given data set, you need to first, the pre-processing of the data is very like important. Like if you have, for example, if you are working on a live data set and you need to work on the null values, so that is, and also you need to work on the feature engineering thing. So after all these things only, we can pass this data, or we can split this data into training and testing test sets. So X and Y, I trained and tested my input and output variables, X train, X test, Y train, Y test. Then I'm gonna create and train the decision tree model, then tree dot model fitting by passing X train, Y train. Then I'm making some predictions, model dot tree model dot predict. Then I'm passing the remaining 20%. And if I wanted to evaluate the model accuracy score by passing the original value and the predicted value, actual input and predicted value. This is how we can evaluate the model. So one being a good fit. So this is how, so if I wanted to plot, so the based on the above, so this is how the decision tree looks like. So this is how we can utilize the decision tree machine learning model. And also next is a random forest. Random forest is assemble learning method that operates by constructing multiple decision trees during training and output the model of the classes classification or mean prediction regression of the individual trees. It's a popular algorithm known for its accuracy, especially in dealing with complex data sets. So reduced overfitting by averaging multiple decision trees. Random forest reduces overfitting and improves generalization compared to individual decision trees. And the high accuracy, it tend to yield high accurate predictions due to the assembled effect and the averaging of multiple models. the combination of all decision tree models will comes to this picture. That is the reason why we will get a high accuracy and robustness. Random forest is robust into noise and outlier in the data. Feature importance. It provides a measure of feature importance which can be helpful in feature selection. So again, it can be used for classification and regression models. So random forest is widely used for classification tasks such as predicting whether a customer will buy a product or not. So something like that, yes or no, something like that. And regressions also, we do have some applications. It can predict continuous outcomes such as estimating house prices based on the various features. Anomaly detection, it can be used to identify outliers or anomalies in the data. And bioinformatics, predicting protein interactions or identify disease genesis, something like that. So it has a lot of applications, this random forest. And this is a sample data set how the random forest thing works. So I just imported a random forest from the sklearn dot assemble. So I'm using the same above data set only. So from the same data set, I can also prepare a random forest model. So random forest model, this is how you can use it, and this is how you can predict the values. So this is my random forest classifier decision boundaries. So this is how you can this the random forest learning model works. So So we just covered supervised machine learning models like linear regression, logistic regression, decision trees, and random forest. So we have a lot of machine learning algorithms. So that it will take a lot of time. If I wanted to cover everything in one video, that will take a lot of time. So that is the reason why I covered majority of the models, starting from linear regression to predict continuous variable like numerical data. So if I have any classification in classification problem, so if I have the binary class classification, then I can use logistic regression. And multi-class classifications, like I can use decision trees and random forest. So that is how I covered main important machine learning models. And also with some sample data sets, I try to predict the outcome, and I try to evaluate the models of all the four machine learning models. And so I have other terminologies where we are gonna use this one hot encoding, standard scalar, feature engineering, cross validation, and also overfitting, underfitting. So we were talking about all these things, right? So I'm gonna explain all these things, why we are using this, and what is the necessity of these terminologies, and what are the uses of these things. So one hot encoding, nothing but is a technique used to convert categorical variables into a format that can be used for machine learning algorithms. It creates binary columns, often called dummy variables, for each categories or classes for the categorical features. So for example, so when we are working on this decision tree algorithm, so I have zeros and ones, right? So in real life, if I am working on a mail, I wanted to predict whether the mail is spam or not spam. So I have a column where the email is a spam or not spam. So with that word keyword spam or not spam, so the model will not be fitted with that categorical columns. It has to be converted, that spam and not spam, into a numerical data, 190, one being spam, zero being not spam. So that is where this one hot encoding, it will convert the categorical variables into format that can be used for machine learning algorithms. So so that is where we will use this one hot encoding. So example use case, suppose we have a categorical features colors with a values red, green, blue. So after one hot encoding, these features will be split into three binary features: color red, color green, color blue. So where each value indicates whether the observed belongings to the category, like one, two, three, something like that we can name. So that is how this one hot encoding will work, by converting categorical into some numbers. And the standard scalar. Standard scalar nothing but is a method to standardize features by removing the mean and the scaling to unit variance. It transforms the data such that it has a mean of 0 and the standard deviation of 1. So basic example is like if I am working on like body mass index, I have a data set for certain persons. I have weight and also height. So I cannot take the direct values like height, it could be in centimeters, and weight is in kilograms. For example, so I wanted to standardize these things. So different value, for example, 172 centimeters, it is measuring in centimeters. That is why the value is 170, 172. And if I wanted to measure the kilograms, kgs, so 172 in kgs, it is very high. So that is why I wanted to scale the values in different units. So that is where the example case is like, if you have a features like income with a values ranging from 20,000 to 1 lakh, applying standard scaler would transform these values to have a mean around 0 and a variance around 1, making the distribution more Gaussian, like suitable for algorithms that assume normally distributed data. So that is how I gave one body mass index. So it basically it should standardize the values. That is where the standard scalar will come. And feature engineering example is like, feature engineering is a process of selecting and transforming variables or features. So basically this feature engineering nothing but, so what are all the input features and what is the effect on output, what is the correlation between input feature and output variable. So that is where we need to select the appropriate features which is affecting my output. So that is where this feature engineering will comes. In the dataset, to improve the model performance, it involves creating new features, selecting relevant ones, and transforming existing ones to make them more suitable for the model. Examples like creating new features like age group from age. For example, I have a list of age from starting from 1 to 100. I wanted to group them, being 1 to 10 in one group, 10 to 20 is one group, 20 to 30 in one group. So that is how. And combining weight and height to create body mass index, or extracting date components, day, month, year from timestamps, or examples of feature engineering. So this is how this feature engineering will work. And cross validation. Example, cross validation is a technique to access the performance of the machine learning model. It involves splitting the data into multiple subsets, training the model on several subsets, and while using the remaining subset for validation, and then the averaging the performance of matrix. For example, I use a train test split, right? So that is where the cross validation will come, and I need to test the data by with the model. Example is like a k-fold cross validation. The data is divided into k subsets, and the model is trained on k1 subset, validated on the remaining subset. This process is repeated k times, with each subset used exactly once for every validation. So that is for cross validation. So I just wanted to explain all these terminologies. We mostly we will use this one hot encoding, standard scalar, feature engineering, cross validation. So we need to import this one hot encoding standard scalar from the sklearn only if I wanted to convert the categorical variables, or if I wanted to standard or scale my features and also my predicted value, something like that. So this is how it will work. So that is what I prepared, basics, like how this machine learning is, what are all the supervised or unsupervised machine learnings. And in supervised machine learnings, I covered linear regression, logistic regression, with some example data sets, and also I prepared a model and also evaluated the model. So this is how we can do some machine learning models with a given data set by performing feature engineering and handling the missing value, something like that. So this is the end-to-end guide for this machine learning. So I hope you got a nice idea after watching this video. You're going to work on different types of data sets to predict the output values based on the output value. It could be a classifier or regression model, something like that. So I hope if it is helpful for someone, then I'll be more than happy. So if you are liking this kind of content, please do like, share, and if you have any questions, please comment. Don't forget to subscribe the channel. So thanks everyone. Bye. We'll meet in another video.